In the fourth part of the lesson, we speak about the Rankine cycle, which is a typical cycle for power generation using pure steam. And as usual, we compare the theory with a practical example using two different models. Let's start. The steam Rankine cycle is very similar to the ORC, the organic Rankine cycle, that we have seen in the previous lesson, with the difference that it uses pure water vapor and mostly with reheating and regeneration. The temperature range is typically much higher, and we represent this cycle in the diagram TS as displayed on the right side. The first transformation, we call this transformation A, from 1 to 2, is a liquid compression, extracting the condensate from the condenser. It is made by a pump. The transformation B, from 2 to 3, is the heating isobaric in the liquid phase, and this transformation is regenerated by another transformation that we will see later on. So this is free of charge in terms of energy. The transformation C is another liquid compression from 3 to 4, and it is made by another pump feeding the boiler from the feed water heater. The transformation D is the isobaric heating from 4 to 5, and it takes place inside of the boiler, including the superheating. Transformation E is the adiabatic expansion from 5 to 6, and this happens in the high pressure turbine. The transformation F from 7 to 3 is the steam condensing, regenerating the transformation B. The transformation G is the heating isobaric from 7 to 8, and it takes place in the re-superheater. Transformation H is the adiabatic expansion 8-9 in the low pressure turbine. The transformation I is a cooling isobaric from 9 to 1, and it happens inside of the condenser. In the picture are represented the cycle phases and also a simplified process schematic with the same numbers for the reference of each process state. We notice that the process flow is split after the high pressure turbine. The amount Y is going to the feed water heater, while only the amount 1 minus Y is going to the low pressure turbine and afterwards in the condenser. The unknown flow Y is found by energy and mass balance. Here we represent, of course, the flow for the unitary mass, but of course the same consideration can be applied for the full flow rate. As example, we consider the Egbin power plant in Nigeria, in Lagos, the module 1. In the video comments and also here we will put a link to the corresponding website. The working fluid is steam. The mass flow rate 627 tons per hour, corresponding to 174.2 kg per second. The net power output is 220 megawatt. The high pressure turbine entry 12.5 megapascal at a temperature of 538 degrees. The intermediate pressure turbine entry after reheating is 3.3 megapascal at the same temperature of the high pressure turbine. The low pressure blade steam is taken at 0.7 megapascal. The condenser pressure is 8 kilopascal and the efficiency of the cycle 36.6%. In the first model we use real gas and reversible transformations. We assume that the expansion of the turbines are isentropic and we neglect the low pressure blade steam. In the second model, still real gas, but the transformations inside of the turbines are irreversible. We assume the expansion of the turbines being not isentropic, but we take an adiabatic efficiency of 85%. Moreover, we add the low pressure blade steam at 0.7 megapascal. In both cases, we keep the mass flow rate declared by the power plant. The charts are built with the program Thermonator, both in TS and pH. We need both charts to see the thermodynamic parameters in the most comfortable way. The gray curve in background represents the saturation region. The states 1 and 2, as well as the states 3 and 4 in the TS diagram, are overlapped, but we can distinguish them in the chart pH. The transformations 1, 2 and 3, 4 are compressions in the liquid region, so the temperature change is negligible, and that is the reason why they seem coincident in the chart TS. On the other hand, also the enthalpy change is small, so the lines 1, 2 and 3, 4 appear vertical in the diagram pH. The isothermal transformations within the saturation region are also isobaric and appear in both charts as horizontal lines. The transformations 5, 67 and 8, 9 are isentropic and therefore vertical in the chart TS, but since the enthalpy gets reduced, they run from right to left in the pH diagram. The bled steam taken after the high-pressure turbine is the unknown Y. We will determine it using the energy conservation in the next slide. To solve the circuit, as we have said in the previous slide, we need to determine the mass fraction going into the regeneration 67,3, and we call this quantity Y. We write the enthalpy balance of the transformations 2, 3 and 67, 3 for the unitary mass flow. Y into H67 minus H3 equals 1 minus Y into H3 minus H2. Solving for Y, we find a quantity very close to 0.3. Let's find now the technical work of the cycle still for the unitary mass flow. The work is the sum of the works 1, 2, 3, 4, 5, 67 and 8, 9. Work 1, 2 is 1 minus Y into H2 minus H1. We get 2.322 kJ per kilogram. Work 3, 4 is 1 into H4 minus H3, 11.25 kJ per kilogram. We notice that both works are positive because this work is given to the system. It is the work of the two pumps. Work 567 is 1 into H67 minus H5, negative 396.5 kJ per kilogram. Work 89 is 1 minus Y into H9 minus H8, negative 879.4 kJ per kilogram. Those works are negative because they are given to the user, and they are much higher because we are in the vapor region. Altogether, the work of the system is negative 1262.3 kJ per kilogram. The corresponding power is the product of the mass flow and the work. We land into negative 219.9 megawatt, very close to the power declared by the power plant for the same unit. Now we need to determine the given heat and efficiency. The given heat is the sum of Q45 and Q67,8. 1 into H5 minus H4 plus 1 minus Y into H8 minus H67. Altogether 2744 kJ per kilogram. The thermodynamic efficiency is, for definition, the ratio between the work and the given heat, and since the work is negative, we need to change the sign. We land to 46%, which is much higher more or less 10% than the efficiency declared by the power plant. Therefore, this model is, at least for the determination of the efficiency, not correct. We start now the second model and we introduce more complexity. The expansions are not isentropic any longer and another bled steam amount X is added. As a consequence, we have 3 compressions and 3 expansions instead of 2. The liquid compressions 1, 12, 13, 2 prime and 3, 4 are only visible in the pH chart and they appear vertical, but actually they are not because there is a slight enthalpy increase. How to determine X and Y prime and also the new states 7 prime, 8 prime, 9 prime we'll see in the coming slide. We calculate first the new exhaust states of the turbine expansion using the definition of the adiabatic efficiency of the turbine itself. H5 minus H7 prime equals efficiency of the turbine into H5 minus H7. Therefore, H7 prime equals 3108.1 kJ per kilogram. H8 minus H9 prime equals efficiency of the turbine times H8 minus H9. Therefore, H9 prime equals 2471.9 kJ per kilogram. Since we adopt now a new regeneration step, the low pressure bled steam 8 prime 13, we introduce another pumping stage. The original pump step 1-2 is now split into 1, 12 and 13, 2 prime. The mass flow Y prime, that is the intermediate pressure bled steam, is calculated by means of this balance. Y prime H7 prime minus H3 equals 1 minus Y prime into H3 minus H2 prime, and we find for Y prime the value of 0.14. All the states common to the previous model have the same number without the apex. The new state 8 prime is found as intersection of the isobaric 0.7 megapascal and the expansion of the second turbine 8-9 prime. The mass flow X, the low pressure bled steam, is found by means of this balance. X into H8 prime minus H13 equals 1 minus X minus Y prime into H13 minus H12, and we find for X the value of 0.145. Let's find the technical work of the cycle for the unitary mass flow. The work is the sum of the 3 compression works 1, 12, 13, 2 prime, 3, 4 and the 3 expansion works 5, 7 prime, 8, 8 prime and 8 prime 9. Replacing the values we find respectively 0.499, 2.476, 11.25, negative 337, negative 231.7 and negative 570.9 kJ per kilogram. Altogether we land to negative 1125.3 kJ per kilogram. The corresponding power is the product of the mass flow and the work, and it is negative 196 megawatt. The given heat is the sum of the heat of the transformation 4, 5 and the heat over the transformation 7 prime 8, that is the reheating process. The result is 2771.3 kJ per kilogram. The thermodynamic efficiency is the ratio among the work and the given heat, and it is 40.6%. If we estimate the efficiency of the electrical generator in about 98%, remembering that there is no gearbox, there is direct coupling, the total efficiency will be 0.406 times 0.98, that is 39.8%, while the total power is still the product of the thermodynamic power and electrical efficiency, also 192 megawatt. What are the reasons for the deviations? The efficiency is 3% greater than the declared one, and the power is 13% less than the declared value. Possible explanations are: we have used a simplified model with only 2 regeneration steps, but actually there are 7, like in the schematic aside. In the efficiency of the system declared by the power plant are always the auxiliaries, and those are not taken into consideration, but they are affecting few percentage units. The flow rate of the steam can actually vary from 170 to 190 kg per second. Therefore, a net power of 210 MW could be achieved in our model instead of 192, and under this condition our error for the power drops below 5%. So as conclusion, our model is not so bad considering the limitation and the simplification that we have made. Thank you very much for your attendance, and remember that reality is complex, much more complex than our models.